Hi, everyone. So I'm going to be doing 3 different problems from the review. I'm going to do one optimization problem, one linearization problem, and then one Newton's method problem. So I'm going to start by doing number 3 because we did a problem like this in class, but it was a little while ago, and I think it's an important one for you to be sure you can understand and do. So in this problem, we have an open top box, which is to be made by cutting squares of side length X from each corner of a 15-inch by 20-inch sheet of tin and bending up the sides. We need to figure out what size the square should be to make the box hold as much as possible. And then what is the resulting volume of the box? So a couple important things I noticed. One is that the box is an open top, so it doesn't have a lid. And it's a 15 by 20-inch sheet of tin. And we want the box to hold as much as possible, and we want to find the resulting volume. So I already had drawn this because I did a demonstration in class to kind of show what this looks like. If you have a piece of paper, you cut a square out of each corner and then fold up each side, it gives you an open top box. So that's when we lay that paper or sheet of tin flat, this is what it looks like. This is what's happening. Those 4 squares are getting taken out and we're bending up each side to make a box. So you should just know that, you know, when you have this kind of scenario, this is the picture you want to make sure you draw. And of course, we need to figure out what we know and what we want to optimize. So for the optimizing part, you want to look in your problem for, are you trying to maximize something, minimize something, and what is it you're trying to maximize or minimize? That is always how you get your optimization equation. So in this problem, it's saying we want the box to hold as much as possible. That means we want the biggest possible volume. So we're trying to optimize the volume. In other words, for this, we're finding the maximum of the volume. Sometimes you need to find the minimum, but in this case, we're finding the maximum of the volume. And we know for a box, the volume is going to be length times width times height. So it's good to write down what you know you need to optimize. Now let's go back to our diagram and kind of label what we know. So we know that the squares have the side length X and it's a square, so all the side lengths are the same. So all these side lengths on the squares are X. And then we also know it's a 15 by 20-inch piece of tin. So I'm going to go ahead and label the width as 15 inches and then the length as 20 inches. And that means we need to use, we need to use the information in the diagram to figure out how to represent the length, width, and height for this specific box. So right now we have length, width, and height as 3 separate variables, but we want to represent them using X because they already gave us X as a variable for the side length of the squares. And that's what we're trying to figure out. It says what size should the squares be? So we're going to have to solve for X at some point. So let's figure out what the length, width, and height are for the box in terms of X. So if I'm thinking about how the box works, I know that the sides get folded up to give me the height. So the height is going to be whatever X is. When you fold up the sides, that part that's going to be vertical is going to be the height of X. So I know that my height is going to be represented by, I'll give myself a little more room, by just the variable X. Now my width of the box is whatever the width is after I cut out an X from both sides. So basically I'm taking that 15 inches and subtracting 1 X on both sides to give me my new width. So my new width is going to be this piece right here, which is 15 minus 2X. So my width is going to be 15 minus 2X. And then my length, similar idea. is we're trying to find what is this piece, which is after you take out 2 x's from the 20 inches. So it's going to be 20 minus 2x is our length. So we're going to represent length as 20 minus 2x. And of course, all of these things are being multiplied together to give us the volume. Okay. So length times width times height. We actually didn't really have an equation for the no here. The no is just like using that diagram to get the length, width, and height in terms of x. Because now we already have an equation we can take the derivative of since it only has one variable. So just to back up for a second, in general, with the optimization problems, you need to find what you know, which is usually oftentimes like if you see them give you like a volume or an area or a perimeter, like they'll give you a number for that. That's going to be your no equation. You're going to set that number equal to whatever formula you would use for that specific measurement. And then what you're optimizing is always what it's telling you you want to maximize or minimize. And then when it comes to the process of optimizing, you are always going to be taking the derivative of the optimized equation. Okay, that makes sense because we want to find the max or min of that equation. And in order to do that, we have to take the derivative, find the critical points, and make a sign chart. So you're only ever taking the derivative of the optimized equation. You're never taking the derivative of your no equation. Your no equation is going to help you to basically get the optimized equation into one variable, which even though we didn't have like a true equation here for the no, that is what we did with the diagram. We used the diagram to get the optimized equation into one variable. So the idea is that you're always using the no equation to get the optimized equation into one variable so that you can take the derivative of the optimized equation. That's always kind of the way it goes. So if I want to take the derivative of this, I'd like to FOIL everything out first to make it a little easier. So we're going to start by doing that. So 20 times 15, that's going to give me 300 minus 2x times 20 is minus 40x. 2x times 15 is 30x. 2x times 2x, that's going to be plus 4x squared. And then I'm multiplying all of that by x. And then I'm also going to combine my like terms, 30x and 40x. So when I multiply by x, I'll get 300x and then minus 70x squared and then plus 4x cubed. So this is much easier to take the derivative of. We just have to use the power rule. Okay. So let's go ahead and take the derivative. When we take the derivative, it's dv dx because we're taking the derivative of the volume with respect to x. And yeah, here we go. So the derivative of 300x is 300. The derivative of 70x squared is 140x. And then the derivative of 4x cubed is 12x squared. So remember, the whole point of this is to find the max volume or what x value will give us the max volume. So to find the maximum of an equation, we find the derivative, and then we want to find when the derivative is 0 because we know the derivative is switching from positive to negative and hitting 0 at the maximum. So I need to set this equal to 0, and I'm going to first put it, I like to put it in order with x squared first. So 12x squared minus 140x plus 300, set it equal to 0. And we need to solve this. So I will tell you, I know that we can't factor this because I already tried. And I think when we did the example like this in class, you couldn't factor it either, which means we have to use the quadratic formula. I suggest not like trying to factor anything out of this. Like I know you can factor out a constant. When I did that, I tended to like make a mathematical error. Like I was doing this earlier for the answer key, and I kept, every time I like did that, I would somehow like not get the correct answer. So I don't know. I think it's just because it's easy to make a math error. I would always go back and realize I messed something up. So I recommend just leaving it like this and putting it right in the quadratic formula, but it's up to you. So I'm going to use the quadratic formula, which you should know. You should have that memorized. So negative b, that's going to be negative 140, which is positive 140 plus or minus the square root of b squared minus 4ac all over 2a. And in the interest of not spending too much time showing you how to put things in a calculator, I already have the calculations done. So I know that when I put this whole portion under the square root into the calculator, it gives me 5,200. So square root of 5,200 divided by 24. And then I can calculate that once with the plus sign, once with the minus sign. And when I put it in the calculator and round to 3 decimal places, I get x equals 8.838 when I use the plus sign. And when I use the minus sign in the formula, I get x equals not negative, 2.829. So these are my critical points that I'm going to want to now use to make my sign chart. Okay. So I'm going to go up here and make my sign chart. And my sign chart, remember, is for the derivative. So I'm trying to find the max of the derivative. So I'm going to put 2.829 and 8.838. Oops. That happens sometimes. 8.838 right here. And then I need to plug in values in between and on each side to my derivative to figure out whether it's positive or negative. So if you plug in, like on the left of 2.829, you can plug in 0 into your derivative and you're going to get 300. So that's positive. You can plug in something like 3 into your derivative. And you can do that. And I think that for this one, it's probably like good to do it in a calculator to make sure. But I'll tell you what I got. So when I plugged in 3, I got negative, and then I plugged in 9 to the derivative and I got something positive. So that gives me my sign chart. And I know that the maximum happens when the derivative switches from positive to negative. It'll look like this. So this is my max, which is what I wanted because I want the max possible volume. And remember, now this is the portion where I'm going to go back and kind of think, what was the question asking me? The question was asking me what size should the squares be and what is the resulting volume. So remember that what we just got here is an x value, which means it's giving us the side length of the square. So I can answer that first question using this information, but then to answer the second question, the volume, I need to actually plug in 2.829 into my volume formula. So first I'm going to write that for the dimensions of the square, it's just going to be 2.829 inches by 2.829 inches. And then for the volume, you just have to plug in 2.829 into the original volume equation. 15 minus 2 times 2.829 times 2.829. And if you do all that, you're going to get 379.038. So the volume is 379.038 inches cubed. Please do not forget the units. That's important. And they gave us inches for this, so don't forget your inches cubed, okay? So that's how we do a problem like this. So this one is really good, important for you to study. All right, now the next one I'm going to choose to do is number 5 to do one linearization problem. Number 4 is similar, but more similar to ones we had already done on the homework. So I'll do number 5. It's the same steps as you would do for number 4. So to find the linearization of f of x equals sine of x at a equals pi, and then I want to use the linearization to approximate f of 3.5. Notice it makes sense because 3.5 is sort of close to pi because pi is 3.14159, something like that. So to find the linearization of the function, I need to basically write in point slope form. the tangent line equation for, I want to find the tangent line equation at pi for sine of x. So I know that I'm going to be putting pi as my x value because I'm finding the tangent line at pi. So one thing I need to do is find the y value of the function at pi. So I'm going to plug in pi, which would be basically what is sine of pi. Sine of pi is going to be 0. So I actually have a 0 here. And then to find the slope, I need to find the derivative at pi. So first, the derivative of sine of x is cosine of x, and then the derivative at pi would be cosine of pi, which is -1. So now I have my equation in point slope form for the tangent line on sine of x at pi. And the whole point of this is because if you pick a point really close to this tangent line on the function, you can approximate the y value of the function at a point very close by using that tangent line. Basically, it uses the idea of local linearity, which is if I zoom in really, really close to a function, it's going to start to look linear. So now to approximate f of 3.5, I'm going to want to plug in 3.5 to my point slope form. I first want to get y by itself, but since it's y minus 0 on the left side anyway, it's just y equals -1 times x minus pi. So I'm just going to plug in 3.5 for x. And then so that I can kind of do this without a calculator. You will have a calculator on your quiz, but you shouldn't really need one for this kind of a problem. But I know pi is like 3.1415. So I'm just going to say 3.142 and round it. So I can kind of do it without a calculator. So to simplify that, 3.5 minus 3.142 is going to be 0 point, and then I can do like 500 minus 142, which gives me, I already did this earlier, 358. So 0.358. And then times -1 means I get -0.358. Okay. So yeah, that's our approximation. And like you're gonna have a calculator. You can use a calculator on the quiz, but you have to show all these steps to use the linearization to approximate. Like you have to find the linearization, you have to like plug it in and show that, but you can, since you have a calculator, I always go and actually do sine of 3.5 in my calculator and like make sure it's kind of close. That way I know I didn't make like a huge error. Like I actually like did my math wrong at first when I did this. I think I wrote 3.358 and then I plugged sine of 3.5 into the calculator and got a negative small number. So I knew I was like made a mistake, and then I was able to kind of fix it and get the right approximation. So I think the calculator is just a good way to check you were on the right track. You still have to show all these steps. All right, I'm not going to do number 6 because there's 2 zeros you have to find for number 6 and it takes a long time. I'm going to do number 7. So to use Newton's method to determine the 5th approximation to the solution of cosine x equals x, that lies in the interval from 0 to 2, and they've given us a first approximation of 0.7. So what I always think about is Newton's method, the whole point of it is to approximate zeros. So I need to make this equation, cosine of x equals x, something set equal to 0. So I can just subtract x on both sides. And that gives me cosine x minus x equals 0. So now I can actually approximate the 0 based on the function f of x equals cosine of x minus x. So I'm trying to find the 0 of this function. And so I've got my initial approximation. That's just a package of 0.7. I've got my initial approximation of 0.7, and I am going to use my Newton's method formula to find the second approximation. And you should know this formula. You should, I'm not going to give it to you. It's not too hard to remember. So to find the second approximation, I forgot I want to use a different color. I need to use my first approximation. So we're always using the previous approximation to find the next one. So x1 minus f of x1 over f prime of x1. Okay, so that means I need to, my first approximation is 0.7, so I'll plug that in for x1, and I need to plug in 0.7 to my function, and then also plug it into the derivative of my function, which we haven't found yet, so let's do that. The derivative of my function is, the derivative of cosine of x is negative sine of x, and then the derivative of x is 1. So I'm plugging in 0.7 into my function first. So I'm not going to show all that. I have it done. But you would have to use your calculator. You definitely 100% need a calculator for this question. So when I plug 0.7 into cosine x minus x, I get 0.064842. And for these problems, we do want to go to the 6th decimal place. I know it's tedious, but on the quiz, I'm going to ask you to go to the 6th decimal place. And then when I plug in 0.7 to my derivative, negative sine x minus 1, I get negative 1.673871. And when I plug this into the calculator, I get 0.73. Nope, I looked at the wrong thing. No, I looked at the wrong part. Sorry. The top was right. The bottom is negative 1.644218. And then when I divide that and subtract it from 0.7, I get 0.739436. Okay, so that's actually already pretty close to our initial approximation. So that kind of tells me I might not need to go that much farther. It did tell us to go to x5, but you're going to see that we don't have to, and I'll show you why. So if I do x3 now, I'm going to use x2 to get x3 in my Newton's formula. So that means I'm doing 0.739436 minus, now I'm not going to write it out again, but I need to plug that into my function to get my numerator. And when I do that in my calculator, I get negative 0.000587. And then when I plug it into my derivative, I get negative 1.673871. And then when I put all of that into my calculator, I get 0.739085. It's crazy because we already have like the same first 3 numbers consistently. So I can tell I'm like really like this is going to be really accurate. If I go on to do x4, since it's telling us to go to x5, I use x3 to get x4. And then when I plug this into my calculator, I'm doing 0.739085 minus, when I plug that into my function, I get something, you'll see you get like 2 point something 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 times 10 to the negative 7th power. That means it's so small, it's like past the 6th decimal place, like it's 0.00000, and then the numbers start, which means it's a really small number. And since we're going to the 6th decimal place, that is so small that it's essentially 0. That you're essentially subtracting nothing from our last approximation. So it's like not going to change this approximation. It's going to change it, but past the 6th decimal place. So we don't even have to go into the 5th approximation or the 4th one. It basically just means that 0.739085 is as accurate as we can get to the 6th decimal place. I had taken this problem from elsewhere, so I don't really know why I said go to the 5th when, as you can see, I mean, I guess if you were doing more decimal places, you could keep going and get it more accurate, but we're only going to 6 decimal places. And because that number was so small that it was 0.00000, and then the number started, there's no reason to even have to go there. It's not going to affect our last approximation. So 0.739085 is the best approximation you can get. And on the quiz, you aren't asked to go past the 4th approximation anyway. So That's all. That's a review of optimization, linearization, and Newton's method, which are the 3 things you will see on your quiz on Monday. I hope this video helped. And of course, let me know if you have any questions, and you can look at the key online to see the answers and solutions and work for all the other problems. Okay. All right. Good luck.